I don't know, fewer than 3 students, I don't think, no. Okay. Especially if they've been gone for a week. All right, we'll go from current slide. And I know you were able to follow YouTube videos while you were gone, right? Of course, big time. Okay, well, I've already marked you present, so let's get going. Any questions on anything before we begin?
No, sir.
Okay. We got up to, we're in section 8.4 on page 546, chapter 8, integration techniques and improper integrals. And we are still in the section on trigonometric substitution. And here is an application of that, and that application is arc length. And that's example 5, which has shown up now. Sorry. This is awful. Okay, find the arc length of a graph. Okay. Oh, okay. Boy, this is the solution. All right. Why was I one slide over? Okay. Say, find the arc length of the graph. F of x is equal to 1/2 of x squared. Sorry. From x equal 1 to, 0 to 1. Now I remember we did get started on this, and I just basically defined the problem here, and that's why I flipped it over one section. Okay. Here's the figure for it and all. So, there is the problem. Find the arc length of this graph. This is 1/2 x squared, just to check on that. 0, 0 is certainly on the graph, and x equal 1. 1 squared is 1, and half of 1 is 1/2. So x equal 1, this is 1/2. And negative 1 would be negative 1/2. I mean positive 1/2 as well. But we're not going over there. We're staying between 0 and 1 on x. Okay, so the arc length is, find the arc length of the curve from 0, 0 to 1/2. 1/1/2. Okay, now, I was starting to proceed, but since they gave it to you, it said, well, maybe we shouldn't. Okay, do you remember what the arc length formula is? How it goes?
I remember doing arc length, but I can't remember.
Right. Okay. It's not something I tend to remember either, except teaching it often enough. It is a weird kind of a formula. But if you think of the arc length, what we approximate it with, let me get my pen set up, is we approximate it by little segments here of, this is your dx and this is your dy, and the hypotenuse of that is approximately the arc length. It's not exact, but then in the limit is dx goes to 0. Of course, dy is going to 0 too, and you'll be very close to the arc length. Summing it up, which is integrating. So basically, this length here is the square root of dx squared plus dy squared. Oops, dy squared, right? And then this is times your okay. That's what that little length is, okay? And here's the trick, okay? Let's divide what's inside the integral by dx, but if you put it inside the integral, that'll be a dx squared, okay? But outside not integral, outside the radical, that would just be a dx, okay? Oops. It's supposed to be an erase, and I didn't hit the erase button. So, divided by dx squared inside the radical, and that's the same as the dx outside the radical. Well, then you put these, dx squared over dx squared would be 1, plus dy squared over dx squared. Now, those are squared quantities. They're not d2x. And this would be dy dx squared times dx. And we integrate that over dx, which is from 0, x is your variable, 0 to 1. What is this? This is the integral from 0 to 1 of the square root of 1 plus f prime of x squared. That's what dy dx is, squared, dx. So, to do your arc length, find the arc length, first thing you got to do is what? What was our Jesus question? Or answer?
Take a derivative.
Take a derivative. So we start by taking derivative. F prime of x is
2x.
Well, this is 1/2 x squared. So 2 times 1/2 is
That'd be 1.
1 what?
That's what I thought would be 2.
Yeah, 2/2 times 1, 2 times 1/2 is 1, and then
That's,
x.
oh, right.
Yeah, reduce that by 1. Okay? So there's what f prime is. But what's f prime squared? That, of course, would be
The x squared.
x squared. Perfect. Okay? Then 1 plus f prime of x squared. No. 1 plus f prime of x squared would be 1 plus x squared. Right? And then we want to take a square root of that. The square root of both sides here. Save me writing some. That's going to be my integral. The integral of from 0 to 1, 1 plus x squared dx. Okay, finally we got there. Okay, so I thought we did arc lengths chapters ago. You know, why are we doing them now? Well, to do that integral, though, no substitution I could think of is going to help us any. No direct substitution. But, what have we been studying in this section?
Trigonometric.
Trig substitutions. Is that one of the forms that we like to see under a radical? If we're going to use a trig substitution.
Yeah.
Actually, remember our forms are 1 plus, or a squared plus x squared, a squared minus x squared, and x squared minus a squared. So this is one of them. Only the a is 1 here, okay? Which makes it pretty nice. Okay? And here's Brian, right? I have trouble reading my lousy writing. No, this is pretty ugly. Okay, we're doing example 5, top of page 546. We just barely sort of got started on it last time. We've been walking our way through remembering how to do an arc length, and our function comes up, our integral comes down, integral from 0 to 1 of square root of 1 plus x squared dx. And as I said, a normal substitution, let u equal blah, 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 isn't going to help us here at all. But the trig substitution has promise. Which trig substitution might you choose? And these are different from before. Before it was let u be some new variable equal to some function of, or some representation of this. Well, now we let the variable here be represented by trig substitution. That's why they call it the trig substitution. Okay? So what would that be? Let x equal, second? Yes, that's the tangent one. Tangent, and what did you say? Theta, is that what you said? Okay, yeah, I couldn't hear, my hearing so bad. Let x equal tangent theta. Then, what do we do? dx is equal to, what's the derivative of the tangent? No, that's the derivative of secant tangent. Derivative of tangent is, stay with secant.
Secant squared.
Yeah, secant squared.
And these from page 541 there?
541, what is, okay, is that where they're doing it?
Like where it has like
Yeah.
cosine squared theta equals 1 minus sine squared theta.
Right, okay. Yeah, but you see the tangent squared theta
Yes, sir.
is secant squared theta minus 1. We're going to get to that in a bit, but what we do is go down to the trig substitution for integrals involving square root of a squared plus u squared, which is what we got, 1 plus u squared. Use the u is equal to a tangent theta, where our a is 1. So it's going to be tangent theta. You see it?
Yes, sir.
Okay. Now, what did I leave off of this? I got it written most of the way, but I need one more little thing there. D theta. Perfect. Okay. All right. Now, we got that part. But what's up here is not just an x, it's a 1 plus x squared. So if x is tangent theta, then x squared is equal to tangent squared theta, okay, and 1 plus x squared is equal to 1 plus tangent squared theta. And what's that? What's 1 plus tangent squared theta? Yep. Go back to that same page you were on. 541, you have to rearrange it just ever so slightly. The little gray box you're looking at. Add 1 to both sides of that last one.
Yes, sir.
Is what?
That's secant squared.
Secant squared. That's your secant squared theta. So this is equal to secant squared theta. Okay? But it's not just a 1 plus x squared, it's the square root of that. So if you put the square root here, and of course that would be the square root there, but the square root here, what would you find that to be? Square root of secant squared theta would be secant theta. Perfect. Now, what I need to do is have some more room to write. So I'm going to come over here and erase our scratch work from before. Is that okay? Too bad I already did it. Okay, never mind. Okay. And I think we did this before, so I think it's okay to erase it. We've already used that. And we can even erase that if we want to. And I think we can erase this as well. Okay. All right. So let's pick up where we left off here. We had this integral. The integral. I'm going to leave off the 0 to 1 for now. Is that okay? Okay. What was our square root of 1 plus x squared? That was? Huh? The square root of 1 plus x squared, when you did this substitution, that got down to being a? Yeah, we did all that, and what is our final answer? Secant theta. Is that what you said? Okay, I don't hear well. Okay, so that square root thing there is just secant theta. Okay, and our dx turned out being what? Yes, secant squared theta, d theta. Well, if I have 1 secant theta, multiply it by secant squared, that'll be secant cubed theta, d theta. So there's our new integral, except we don't have the limits on it. Okay? So let's back up a bit. The 0 and 1 are our limits on x. Okay. But we're looking now for thetas. So when x is equal to 0, what tangent of what angle is equal to 0? 0. So the theta becomes a 0. That's good. And when x is equal to 1, tangent of what angle is equal to 1? Pi over 4. So now we have our new limits. Okay. Now we're left with the problem of integrating a secant cube theta. Now we can go back to the last section we did, which was trigonometric integrals, and reproduce all that if we wanted to, or, this is sort of my favorite, look it up, okay, in a trig table. I mean, not a trig table, a integral table, okay? And, oh, y'all don't have books with you. Oh, you do, okay. If you go to the front inside, page of your text, it's not here. There's integral of secant and integral of secant squared, but not integral of secant cubed. I was hoping to see a secant to the nth, and let me make sure I didn't see one. No. Okay. Let's go to back inside cover, and it's further in than that. Before the answers, there are some appendices back here. Do I have it marked here? Oh, there we have. I had it marked on page A3, which is appendix 3, but it's the B appendix. A appendix was proof of selected theorems. This is the B one, and what we look for, forms involving, actually they have the one that we're looking for right there, but let's go to the one that says forms involving tangent, cotangent, secant, and cosecant, and this is on page A5, and find our secant in U. That's what we're looking for. Okay? Now, I'm going to write that down here. I'm going to write it up here, I guess. The integral. This is number 69 on page A5. Integral of secant. I can't write. To the nth u du. Now, what is our n? 3. Okay, so let's make this a 3. Okay, and their answer, everywhere we see an n, we're going to put a 3. Okay, that will be secant to the n minus 2. And if n is 3, n minus 2 would be 1, so that would be secant. And I'm going to change the u to theta. Is that okay? Okay. Secant theta times tangent theta over what's n minus 1? 2. Got it. Okay. And then we have a plus, and the coefficient outside the integral is n minus 2, which is 1, over n minus 1, which is 2, times the integral, same integral, and we'll put the same limits, 0 to pi fourths. Okay. Secant to the n minus 2, and that is 1 secant theta d theta. Say again? Oh, okay. It can't, yeah, okay. Yeah, when I move the thing and when I try to write on it, it's flopping. I'm trying to hold it. When I do that, sometimes short something and it cuts it out, but then it usually comes back. Okay. Well, we got the first part of it okay. So I'm going to write that part down. That's equal to secant theta tangent theta over 2. Now we got to evaluate that from 0 to pi fourths. Okay, and then we have plus a 1/2, and then we have the integral of secant theta. Well, what in the world is that? If you go back up to number 61 on that same page, you see the integral of secant u du is, now I've got my 1/2 there, so it's just this part here. This is log, natural log of, and they put absolute value. We'll see that's not really necessary in this case, but I'm going to put absolute value of secant theta plus tangent theta. Okay, and they have a plus c, but we don't need that because we have our limits. So this is, we have our limits, 0 to pi fourths, which we already determined. All right, so now it's time to write down the answer. Secant of pi fourths, anyone know what that is? Square root of 2, perfect. It's 1 over cosine. The cosine of pi fourths is root 2 over 2, which is 1 over root 2. The reciprocal of that is root 2. So we have a 1/2 out front times a root 2 for the secant theta. What is tangent of pi fourths? 1. Okay, we don't have to do anything with that. And then we do minus 0. Okay. And even though secant of 0 is 1, tangent of 0 is 0, so that one goes away. Okay? Plus, okay, 1/2 again, log of absolute value of secant, again, of pi fourths is, we just said it, square root of 2 plus tangent of pi fourths is 1. So it's log of square root of 2 plus 1. And then we do the minus the log of, and this is all the 1/2 is in front of all this. Secant of 0 was 1, okay, plus, and tangent of 0 is 0. What's the log of 1? 0. Through with that. So what do we have as our answer? Root 2 over 2, that's from the first part, plus, this is from the second part. Get out of there. Okay. 1/2 the log of root 2 plus 1. Oh, and why can I justify forgetting about my absolute value bars? These are both plus positive numbers. Root 2 is positive, 1 is positive. They added together, that's going to be positive. So there is our answer. Okay? Whoa. All right. Let's go back to our problem here, and we have 1/2 of root 2 plus log root 2 plus 1. So they took the 1/2 outside. So it doesn't really matter. That's perfectly fine. If I can find what I did with my pen here. So what they did, and this answer is perfectly fine the way it is, but I'm just going to show you pulling the 1/2 on the outside. This would be root 2 plus log of root 2 plus 1. Okay, and that's what they have. And they even approximate the answer about 1.148, which is a perfectly fine approximation. It'll tell you much more than we had before, but it's short if you write. So if you prefer that. But you had to write the other things to get there. Okay, make sense? All right, let's see how they did it. They started with the arc length formula, which we derived, okay? The arc length S is what they usually call it, is the integral from 0 to 1, because those are the limits on x, of the square root of 1 plus f prime of x squared. So the first thing you got to do is figure out what f prime of x is. It's x, because our f of x was 1/2 x squared. So we had already done that before you came in. So f of prime of x was x, square that, you get x squared, add 1 to it, you get 1 plus x squared, put it all under a radical, that's our integral. And that's where you came in. Can't do much with that by a traditional substitution, let u equal some function of x, not going to work. But if we do a trig substitution, because this is of the form that it suggests we do, excuse me, lunch is not agreeing with me. That would be let x equal tangent theta, and then take the derivative of that, you get secant squared theta d theta, and then do all the things we did, and suddenly they come up with this answer, just out of the blue. But you can do that and see, and the a and b, the limits are 0 to pi fourth, which we saw how that came about, and the integrand is secant cubed theta d theta, which we saw how that came about. Okay. And then they miraculously come up with that answer without telling you how they did it. They probably looked it up in the table too. This is the first part, and this is the second part with the integral of secant theta in mind, and they already pulled out the 1/2 that was common to both of them. And then evaluate this at pi fourths, which, like you said, this is root 2 times 1, so that's root 2, and this is root 2 plus 1. And the 0 here is going to be a 0. The 0 here will be a 1 plus 0, but log of 1 is 0, so that also disappears. And so you just have 1/2 root 2 plus log of root 2 plus 1. All right, which is what we got. 1/2 root 2 plus log of root 2 plus 1. And that's approximately 1.148. Now, I kind of like to go back to the picture. Whoa. I'm going to erase all this if that's okay. It's easier to see. Okay, now, here's where we see, does our answer make any sense? Well, this length is obviously 1, right? So this length, since it's curved, but it has the same beginning point and, in a sense, the end point, then it's got to be a little bit more than 1. And not much more than 1, 1.148. I can buy that. Okay, that looks like a reasonable answer. If you come out 7.3, I'd say, ain't no way. Okay, or 0.7, it's got to be greater than 1. So that answer to me gives me warm and fuzzies inside, so I feel like it's probably okay. All right, any questions on that? All right, and then they proceed to skip example 6, which if my memory is right, this is a truly obnoxious problem, okay? That they don't even do, they say, the details of the integration are left for you to complete in exercise 64, intuitively, blah, 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 blah. So since they don't finish it for you, I'm wondering if we ought to even pursue it. What you think?
It's pretty hairy down there.
It is a little bit. It really probably isn't quite as bad as it looks, but it will take time. Do you want to take time to do it or not? I'll be glad to at least give you a bird's eye view of it once I get Daniel here. Speaking of bird's eye views. Okay. So, want to see one like this or not? Yeah? Okay. Let's go for it. All right. This is example 6, bottom of page 546, chapter 8, integration techniques and improper integrals. This is the very last example in 8.4, trigonometric substitution. Here's what we got. A sealed barrel of oil weighing 48 pounds per cubic feet. That's the oil's density. Okay? Is floating in seawater weighing 64 pounds per cubic foot. It's also a density in U.S. customary measures. Okay? The barrel is not completely full of oil, so with the barrel lying on its side, the top 0.2 feet, my throat's breaking up on me. The top 0.2 foot of the barrel is empty. I think, yuck. Yeah, that is what they mean. I was thinking, when you set the barrel upright, because then it makes more sense to talk about a foot. When it's on the side, you've got a curve there, and are they talking about that much? Indeed, in the picture, that's what they are talking about. Okay, so with the barrel lying on its side, which is, they were explicit in that, the top 0.2 feet of the barrel is empty. Okay. I was going to say they have not really given you enough to really do the problem, but at the very end they do. It says compare the fluid forces against one end of the barrel from the inside and from the outside. Assume the radius of the barrel, this is where I was going to say they didn't give you enough information. Assume the radius of the barrel is 1 foot. Radius is 1 foot. And with the barrel lying on its side, the top 6/10 of the barrel is above water. Yeah. Okay. Okay. I guess I need to draw some of this, but that really stinks. Okay. I'm not going to draw the barrel in the water on its side. I'm just going to do the end, because that's what they're asking for. If that was indeed a circle, which probably brings a lot of laughter to everybody, remember they said this is a 1 foot radius barrel. Radius. So this would be, if you put the origin at the center of that, this would be 1, 0. This would be 0, 1. This would be 1, 0. Yuck, I say 0 and write an 8. Where in the world did that come from? Okay. I don't even know what I was thinking to get an 8 out of that. it's -1, 0, and 0, -1. I was explaining to Clark before. This morning, just middle of the morning, feeling good. All of a sudden, my head just started draining like crazy, and now it's completely clogged up. So I'm having trouble breathing and clearing my voice, so sorry about that. So here's the picture, okay? Now, the first thing it's the last thing they tell you, this is 1 here. That would be a half. That would be a fourth. Let's see, 1, 2, 3. Need one more somewhere in there. Something like that, okay? So 1, 2, 3, 4, 5, 6. So here is the part that's submerged underwater. It's 0.6, the top 0.6 of a foot. Oh, yeah. Sorry, I did it backwards. Okay, let's try that again. The top 0.6 of a foot is above water, meaning 0.4 of a foot is below water. So here's the water line. This is this, I believe it's salt water, didn't they say? Seawater. And the density of the seawater they give you. Okay. Rho for seawater is 64 pounds per cubic feet. Yeah. All right. Now, the top 2 feet of the barrel is full of air. Okay. So in here we have all air. In this portion right here. Okay. Sorry, my pen drug there. I was trying to figure out where in the world that came from. Okay. All right. Oh, man. And the other thing they said, blah, 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 blah. Yeah, assume the radius of the barrel is 1 foot, which we've been assuming, which means the limits here is x squared plus y squared is equal to 1. That describes the supposed circle I have there. Okay. All right. To find the fluid force against the end of the barrel from the inside, the integration goes from -1 to 0.8. So you would be, the pressure on this lid here, the circular lid, would be all this here. So it'd be from -1 to 0.8 because it's 2/10 from the top. So there's the fluid there. The oil, the density of the oil, rho of the oil is 48 pounds per cubic feet. Let me erase that. Okay. Now, okay, your what we're going to do is do dy's. That makes the most sense, right? Okay. dy's here. The y is going from -1 to 0.8. Okay? They've already sort of given that away. Okay? Now, your incremental at an equal pressure. Now, this is the again, the question is, compare the fluid forces against one end of the barrel from the inside and the outside. So we look at the fluid force from the inside where the oil is pushing out. Okay? So the fluid force from the inside, and remember what force is it weight per unit volume. Okay? No. Density is weight per unit volume. So we know the density. Okay. Take this over. Pressure is pounds per area. So pounds per square foot we'll use because everything's in terms of feet here. Pounds per square feet. Okay. It's not a huge mystery what the square footage of this is. It's not trivial, but it's not that bad. But so you got to get the total force on that side. So that's what we're going to do first, is the force on the inside of the barrel. And then we'll divide that by its area, and that'll give you force per square foot. Okay? Now, what is the force on the inside? Again, let's take little strips, dy. Yeah, I can't get my pen. Let's just take a typical little strip here, dy. Now notice I'm only going to do 1/2 of it. So this is your dy here. Okay? Now, where are you going from? Well, you're actually going from one side to another. That's exactly twice from the origin, from the y-axis to the side, right? So I'm going to simplify things and just do 2 times that. Okay. Well, where is this going to? Again, x squared plus y squared is equal to 1. So at any given y here, y squared is equal to 1 minus x squared. Okay? See, is that the way we want to do it? I think we want to do it another way. X squared is pause and think for a moment here. I think we want to get everything in terms of y. Yeah. And then the length of that would be your x in terms of y. So x is equal to the square root of 1 minus y squared. So this value x here, x is equal to the square root of 1 minus y squared. Now that works for up here or down here. Because this is y is equal to 0. That's why choosing that is important here. And down here you have negative y with a negative y too. So I think that works fine. Okay. So that's the length. The width is dy. The density we know, 64 pounds per cubic feet, pounds per cubic foot. And our limits from from negative 1 to 0.8. So I think that gives us everything we need. The total force inside the barrel is the density, which is a constant, 48 pounds per square foot. I'm going to write this for now, just so times the integral, and this gives us our because density is force per unit volume, so we what we've got out here is the volume, okay? And the volume is that strip times 2, so I'm going to make it 96. Yuck. Probably goes out. It'll come back, I hope. Yeah. 96, because we're only doing 0 to here, doubling it. Okay, so the volume of this, and I hate to call it volume. It's not actually a volume. Because we don't know the length of it. So we're only dealing with an incremental part. All right. All right. Okay. They throw in an h of y here, and they don't really tell you what that is. You sort of have to go back to what you were dealing before when we were doing these kind of problems. And the h of y is the height as a function of y, okay? But since you put your y0 being right here, okay, the h of y, I'm going to write it in here, h of y, and then multiply that by the, what they call the L of y, I think is what, yeah, where the L of y, I hate their doing that, okay. It's the height times the length times the thickness, and the dy is the thickness, okay. So, that's what gives you cubic feet. How high you are, length times the, and frankly to me, the integral of dy seems like that would take care of the height for you, but there, you've got to have the function in there. Okay. So what is the height here? The one I drew here would be 0.8 minus y, right? That's the height we're talking about. Height of liquid above this element. Okay? I think that's what the, yeah, 0.8 minus y. So when the y is here, 0.8 minus y. When the y is down here, it's the 0.8 minus a minus y. So what you're doing is summing all these heights. Now the reason for this is they have different it's the equal pressure at a common height, and so that's why you have to put the h and y in there. Like I said, this problem gets to be really messy. So this will be for us 96 pounds, and I'm going to leave these off after a while, per cubic foot times the integral from minus 1 to 0.8. The h is 0.8 minus y. That's the height function. The length is, this one I just said, that's the x value, which is the square root of 1 minus y squared, and then you got your dy. So there is your function, okay? Now, what they do is split that into 2. You multiply your 0.8 times this, and that gives you a different coefficient out in front, 0.8 times that, and that's where they get that, minus this times that. Well, that first one is one that you need a trig substitution on. The second one you don't. You use just a regular substitution. And that'll give you the inside. Then you got to turn around and do the outside too, But the outside, you're just going from 0 to 0.4, negative 1 to 0.4, but you do the same type thing. Your density is different. It's sort of a similar type problem, just with different numbers in them. And you go that way. So it says the details of the integration, which I hope I've just sort of described for you, left for you evaluating these two integrals. They say the force from the inside is 121.3 pounds, from the outside is 93.0 pounds. Which seems to indicate you would tend to bulge out the top and the bottom of the barrel. But the details just take way more time than I think it's worth. But I just sort of outline for you how you do that. Then you do the same thing with the from the outside. Only your limits are different. Your densities are different. But other than that, the problem sort of stacks up the same. So I'm going to leave that, as a lot of mathematicians will say. We'll leave that for the student, so I'll let you work on that. If you have any questions on it, bring them. We'll take more time to do it, but it is sort of a pain in the neck type problem. Oh, that was forces inside and outside. When you do force per unit area, though, and they didn't ask for this, but if you did force per unit area, then I think you would find out the pressures are equal. So you don't really have bulging out. You would think you did, but because the inside is acting over a bigger area and the outside is acting over a smaller area, the bigger force, of course, would be divided by a bigger area, smaller force by a smaller area. I think you'll find the pressures are very equivalent. Maybe not exact, but pretty equivalent. A lot better than the numbers indicate, the force numbers. And that's why I wondered, why in the world are you comparing those forces anyway? Well, good thing to compare, but I mean, what's the point of it? All right. So homework exercises here, do either 3 or 5 or both. They're both should be at calcchat.com. Do either 7 or 9. They're both at CalcChat. 7's at CalcView. Do either 11 or 13. They're both at CalcChat. 15 or 17. They're both at CalcChat. Any of the odds 19 to 31. They're all at CalcChat. 19's at CalcView. Do either 33 or 35. They're both at CalcChat. 35's at CalcView. Do any of the odds 37 to 41. They're all at CalcChat. 37's at CalcView. You can explore doing 43 and or 45. They should both be at CalcChat. There's true false, 47 or 49. Good to think through and then figure out on CalcChat why they're true or not. Okay. 51's a good area problem. It should be at CalcChat. 53's an arc length problem. It should be at CalcChat. Volume of a torus is 55. That should be at CalcChat. 57 is a centroid. That should be at CalcChat. Any of the odds 59, which is not too different of a problem from the one we were just doing. 61, a tactrix, okay, I don't know how to pronounce it. Do either one of those two, or both if you choose. They should be at CalcChat. 63 is a fluid force problem, and it's at CalcChat. And then I would say either 65 or 67. They're both at CalcChat. Okay? And they're talking about a loom there, which is an interesting concept. You would think it sort of came from moon, which I wouldn't be surprised if it didn't, but I'll let you work on that one. Putnam challenge is usually pretty hairy, so if you want to give that a shot, you certainly can. All right. Any questions on those? Skipping that last one, the ugly, gory details of it, but let's go on. So, okay, to move on. All right. Now, we did trigonometric integrals, then we did trig substitution, integration by trig substitution. Oh, and earlier we had done integration by parts. Was that last term or was that this term? That was this term, wasn't it?
That was the first thing we did.
Okay, that's the first one we did. Okay. So now we're ready to 8.5, which is another technique. And this is called partial fractions. And if you love fractions, you only partly love partial. No, I'm just kidding. Okay.
How far are we going with the chapter?
Okay, good question. We're doing 8.5 for sure. Okay. 8.6 is numerical integration. And let me see. I ought to at least introduce you to that. Yeah, and then integration by tables, and we'll do that. That's definitely need to. We've already been doing it. But, and improper integrals, I think if I'm not mistaken, I'll leave that one off because technically it's not an accurate integral, but you know. So yeah, we're going through 8.7, but not 8.8. So let's go this from current slide. So chapter 8 again is integration techniques and improper integrals. We're just going to do integration techniques, not improper integrals. Here's another technique, which is partial fractions. Okay. Objectives of this part. He's getting tired. Understand the concept of partial fraction decomposition, which, go back early in your math days, you really were doing something like this. We use partial fraction decomposition with linear factors to integrate rational functions, and we use partial fraction decomposition of quadratic factors to integrate rational functions. So we're going to do two types of rational functions, linear factors and then quadratic factors. So we'll do some of all of these. And let's start with what in the world do we mean by partial fraction? Procedure for decomposing a rational function into simpler rational functions. That's what we mean by partial fractions, to which you can apply basic integration formulas. That's the method of partial fractions. To see the benefit of this method of partial fractions, let's consider this integral. You think you can do that by any other way that you know so far? Direct substitution isn't going to do you because you need a 2x minus 5 in the numerator. You don't have it. It's not set up for a trig substitution. If you tried one and worked at it hard enough and miserably enough, you might come up with something, but it's going to be pretty ugly and nasty. Okay? Now, if I didn't have the integral signs here or the dx there, and just that was a problem. I didn't tell you anything else. Oh, maybe simplify that. What would you do to simplify it? Forget the integral sign, forget the dx sign. It's that simple. Second, factor to the bottom, okay? Remember the F word, okay? Y'all know the F word, right? Factor, okay? In this course, it's always factor. Okay, so let's factor that. All right, if it's factorable. Now, if it's not factorable, you may be in serious trouble. But this is factorable, I think, isn't it? What would that factor as? X times X. What'd you say?
X minus 3.
Minus 3.
And X minus 2.
X minus 2. All right, so this fraction here would be the same as that fraction, wouldn't it? Okay. Now, this is going way back in math, and hopefully it's not too confusing. If I had 1 over 3 times 2, okay, number 1, that's 1 over 6, right? But that's also some relation between 1/3 and 1/2, isn't it? Okay? Would you say?
Yes.
Okay. Because you're combining these two things together, and in fact, just looking at this, I know it's a plus here and a minus there. That's going to give me 1/6, right? Because 1/2 is 3/6 minus 2/6 is 1/6, right? In a sense, what I did was take a sort of big denominator, split it into its factors, and come up with two simpler fractions, right? Now 1/6 is pretty simple, okay? But when you get something like this, ooh, if I can get this into 1 over x minus 3, or something over x minus 3, and something over x minus 2, I can integrate those two. I can't integrate that. But I can integrate something over this, that would be a log of this. And something over that would be a log of that, right? So that's the deal. Can we somehow get that fraction to simplify, and this is the first step, into some combination of fractions with those denominators? Okay? So here's what we're going to do. Let's say this is some a over x minus 3 plus b over x minus 2. Now, do you want to go up and do the 1/6 that way too, just to see how it works? Because we know what the answer is going to be. Let's see if we can do that. 1/6 is equal to a over 3 plus b over 2. Right? We should be able to decompose that 1/6 into some sort of thirds and halves. Okay? Now, what would you say a good first step to that would be if you're trying to find what a and b are in that problem up there, the one up there, the easy one? What would be your first step?
Get a common denominator.
Well, what would it be? 6. And what would you do with it? You got it. What do you do with it? What don't you like about that?
A and B.
Oh, I like a and b. I just don't like fractions. Oh, I'm sorry. I shouldn't say that, should I? So how do I get rid of my fractions? Lose my denominators, and they won't be fractions anymore. So you found the least common denominator. What can we do? Not divide. It's already divided.
Oh, yeah,
Multiply. Let's multiply both sides of this equation. In other words, every term on both sides by 6. This by 6, this by 6, and this by 6. That's legal in most states, right? Because you're multiplying the same thing by both sides of the equation. Perfectly fine, right? So what do we have? We have this goes to 1, this goes to 2, and this goes to 3. So what do I have here? 1 is equal to 2a plus 3b. Okay? Now, this looks like it's not fair to do, but it's okay. Let's just say, what if b were equal to 0? That's not quite what I want to do. Then a would be 1/2. And if a were 0, b would be 1/3. There I got my fractions there, but the signs aren't quite right. But you see, there is a way to get there. Let's not mess with that too much more. Let's come back to this. That's not quite how we want to do it, but it would start to get us there. First thing we would do down here then. What don't you like about it? The denominators. So how do we get rid of them? Yeah, multiply by x minus 3 times x minus 2. X minus 3 times x minus 2. That's times 1. This is times x minus 3 times x minus 2. And this one's times x minus 3 times x minus 2. Okay? Now, here, the x minus 3's go out, x minus 2's go out, you're left with 1. Here, the x minus 3's go out. That is equal to a times x minus 2. Here, where x minus 2's go out, and that gives us a plus b times x minus 3. Right? Now, that should be good. Those equations should be good for any x's, right? So let's pick a couple of really neat x's. This is the part that doesn't seem fair. And I'll tell you why it doesn't seem fair to me, but the trouble is it works. So fair or not, it works, okay? What's an easy x to choose this to be?
0.
To choose x.
1.
To make that 0.
Oh, 2.
2, okay. So let's say for x equal 2, what do we have? 1 is equal to, this goes away, doesn't it? And you get b times, when x is equal to 2, 2 minus 3 would be negative 1. So b is 1 is equal to negative b, so b is equal to negative 1. Ha! Okay. Well, how about give me another one? That would be a pretty easy one.
3.
Yes, let x equal 3, then this goes away, and what do you get?
1.
A is equal to 1. Perfect. A is equal to 1. Well, this suggests to you that 1 over x minus 3 minus 1 over x minus 2 should equal 1 over that mess that we had to begin with. X squared minus 5x plus 6. Okay? And if you want to be convinced of that, multiply these two together, and you get that. And to do that, you need to multiply this one by x minus 2 over x minus 2, this one by x minus 3 over x minus 3, x minus 2. So then you get that as your denominator, and this will be x minus 2 minus x minus 1, which is x minus 2 minus x minus 3. Okay? Well, the x minus x goes out, and minus 2 minus the minus 3 is plus 3. That's sure enough. Okay. So yes, that does work. So now, since we know that, okay, keep in mind that, I'm going to erase everything but that last little bit down there. So I'll go on and erase this because we don't need that. That was my example, which didn't really pan through completely. Okay. And we'll erase this part because that's in my way. And we'll erase this part because we've already used that. We got our A and our B. So this thing this big old denominator we had here. I'll go on and write that in. I didn't want to, but I'll do it now. That's x squared minus 5x plus 6. Okay, and since that, left with one hanging parentheses I did not need. Okay, so what this becomes, the integral of 1 minus x minus 3, 1 over x minus 3 dx minus the integral of 1 over x minus 2 dx. That's exactly the same as that, right? And what is this? I can't do this integral, but I can sure do that one. What would that be? That first one. Anybody? The first integral there. Second?
You said the first integral.
Yeah, that one right there. You want to do that?
Is that one x minus e?
This is
X minus 3.
x minus 3 dx. Over there is x minus 2. Just took those two things, split them up, right to each other.
Should it be x plus 2?
It's what?
Should it be x plus 2?
It won't be x plus. Oh, you mean make this a plus and make this 2 plus x? I mean 2 minus x? You could do that, but I don't see why you want to do that.
Why is it?
That's all right. Do this integral. This
Oh,
is the
minus
doable
one.
integral. Huh?
I thought that the factor was x minus 3 and x plus 2 is x minus 3, x minus 2.
Okay. What is this? I didn't hear.
No, I just factored wrong.
Yeah. What we did, we had found out this, put sign of that. So put an integral sign in front of this, and we'll put one in front of each of those, and that's what we got. Okay. The question is, what is that integral of? What is that integral?
Is it the log of
Natural log of x minus 3. That would be natural log. Now, when we do natural logs, we usually put them in absolute values because you can't take the log of a negative number. So we'll do x minus 3 minus the natural log of, help me, x minus 2, and then we need our plus c because it's an indefinite integral. There we have it. That is your answer. Okay? I don't know of any other way to get there except partial fractions. Now, we did way more than they were asking us to. They just wanted to consider that integral, and let's see what they do when they consider it. To find this integral without partial fractions, you can complete the square. Oh yeah, this is the thing I said you could do if you wanted to, and I was hoping you didn't. And that would be this thing here. Oh my word, what a mess is this. Okay? And it is doable. Huh. Oh, no, awful. Okay? But it's doable. You want to do it that way? Or is it just partial fractions? Much better. Okay. So there are two ways. Okay. But man, what a mess that is. Okay. Oh. And here's how you get from that answer to the answer we got. I like the way we did it better. Same answer, much easier slugging the other way than this way. There's way more opportunity for a lot of error there. Awful, awful, awful. Okay. Now suppose you had observed first that, this is what we observed, that denominator can be factored, 1 over x minus 3 and 1 over x minus 2, And then I showed you how you came up with that. They just out of the blue say, hey, this is that. Well, how did they get that? Well, I showed you how we got it. Okay. And we wound up with that same answer in much less writing. And I'm lazy. Okay. So this method is clearly preferable to trigonometric substitution. Yes, yes, yes. Its use, however, depends on the ability to factor the denominator. You've got to be able to do that. And to find the partial fractions. There they are. We know from algebra that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. Yeah, we knew that, didn't we? Way back. Way back we hit that. Pre-calculus algebra, Math 112. Okay. For instance, that polynomial there, oh my word. And here they write it. I hate it when they do this. Okay, let's ignore what they're doing. Okay? Ignore the bottom part of the page here. Pretty much completely. What did they do? Well, they said, let's do grouping. Right? Remember, a 4-term polynomial, that's the only way we can factor it, easily anyway. Will this first group have any common factors?
Yes.
What?
X for the fourth.
Okay. Times x. If you factor out x plus x to the fourth from the first term.
I have a plus 1.
Plus 1. Okay. How about that second group?
No.
Yes. Factor out a minus 1.
Oh.
And what do you have left? X plus 1. Now you have two common factors. They happen to be binomial. And this will be x to the fourth minus 1 times x plus 1. Right? X to the fourth minus 1 have any common factors? I mean, not common factors, any factors?
Yes.
How?
The x squared, x squared plus 1, and then x squared minus 1.
And then that's times x plus 1. Got it? And then, does this one be factored any further?
Yes.
Nope. Sum of two perfect squares, never.
Okay.
So that remains an irreducible quadratic factor, x squared plus 1. But the second one, what will that be?
The x plus 1, x minus 1.
And then we have another x plus 1 here. So actually this one be written a little simpler. It's x squared plus 1, irreducible, times x plus 1 squared, because there's two of those, times x minus 1. So there is a series of, it'll come back, okay, of linear and quadratic, irreducible quadratic factors. Linear, square root of a linear, and irreducible quadratic. Yep. Same thing they got. See how it works? Now, change one sign here or there, you can't do it. Okay. If that first x here would have been a plus, there's no way. No way to do it. Okay. But those linear factors may have radicals in them, which are really awful. We're going to stick with those most of the time, though. We'll have just integers in them. Okay. Okay. And by the way, I skipped right over, I think, yeah, a thing on John Bernoulli. Now, this is interesting. They call him John. Most text, he'll be Johann, okay, which is John in whatever language that is, Italian or whatever. It's hard to tell with the Swiss. Some Swiss speak Italian, some speaks French and some speak German. Switzerland is kind of there in between all three of them. So, which Bernoulli sounds awfully Italian to me, and his nose even looks a little Italian, so it's hard to say. But he's usually Johann. Okay. There's several features here. One, and they don't mention it here, he had a brother named Jacob Bernoulli, if I'm not mistaken. I hope I got it right. And they probably had a different pronunciation, spelling in Italian or whatever. In fact, Jacob is probably, okay. So anyway, those two brothers were both brilliant mathematicians and good physicists too. I mean, really, they were two really brilliant. One of them, I think it was John, but I'm not sure, Johann, he had several sons. At least one, I know, was another brilliant mathematician and physicist. And I can't remember the whole story, but there was this prize. Every now and then, Europe would get together and decide on a prize. They give a prize for someone who could solve this really complicated thing in the most simplest, most approachable form type thing, So there was this contest going on, and he was honcho, top guy around. Figured his only competition was his brother. His brother wasn't even bothering with it, I think, this time. So he thought he had it knocked. And they awarded the prize to his son. Proud father, so proud of his son for doing so well. He kicked him out of the house, They were not a very functional family. They competed like cats and dogs. Brothers, uncles, nephews, sons, fathers, but they were brilliant mathematicians. So brilliant was he that one of his students at University of Basel was Leonard Euler, that we talked about before. So, I mean, these were top science guys. So anyway, if you want to write on any of the Bernoullis, or the relationship, or anything such as that, there's a potential paper topic, as well as Euler, which you could do tons of different topics on Euler. Okay. So, now, let's take this very problem that we have here. Let's see if they give it on the next. Yes. This is exactly what we're going to do. Since we found out a way to factor this denominator, we're going to say, is there some numerator which can be a function of x as well? It doesn't have to be just numerical. It's some function of x. And here's the reason for that. Can we factor this? We already factored this to x minus 1 times x plus 1 squared times x squared plus 1. Remember we did that in the previous slide. Okay? So can we break this down into some a over x plus 1, x minus 1, plus b over x plus 1, but this is squared. We'll then do another term for c over x plus 1 squared, but then for this one, which has a quadratic in it, then you have to have a numerator with an x and a constant term here, so dx plus c over x squared plus 1. Now, they haven't explained to you why, but this is exactly the approach that you do. If you have a single factor by itself, just do a constant over that factor, a linear factor. If you have a linear factor raised to a power, then you have to have a separate term for each power that makes this. So it would be x plus 1 times x plus 1 squared. So one for each. And it's just linear, constant numbers over each of those linear factors. Even though this is a quadratic factor, you don't need x there. But this is an irreducible quadratic, so you do need an x term and a constant term. Now, theory we talked about said any polynomial should be able to be broken into a series of linear factors and irreducible quadratics. Understanding that you can have irrational numbers and all sorts of mess in there, but it can be done. sometimes very difficult. This one was relatively easy to do, so we got it. So this is the form we have. Now, how do you think we're going to solve, figure out what single numerator you could put here, break that numerator into pieces there. Now, and by the way, most of the time you'll know that numerator, but it'll only be some factor of x, and yeah, and that's all you're worried about. But so let's break this down. What do you think? Okay, this is really hard to do it with it being n of x. But what would be your first step? Anyone want to make a suggestion?
Not try to separate them like they are, like when we use our factoring.
Yeah. What we'll do is multiply everything on both sides of the equation by this big old factored formula. So on this side, all you have left is n of x. The whole thing goes out. On this term, only that goes away, and the n times this, the a times this will be left here. But that denominator is gone. And with this one of these goes out, because you multiply by this, and that one stays, and the quadratic stays, and that's multiplied by b. Okay. Then the c here, when you multiply that by this thing, the whole square term goes out, and you're just left with this term and that term, times c. And then when you multiply this by that, these terms go away, and you're just left with these two. That thing times those. Now that's kind of a mess. But you can clean up some of that mess by setting x equal to 1. Now here's the part that's not fair, in my mind. Because x can't be equal to 1. It's in the denominator. But once you get rid of it, you can pretend it's equal to 1. And it works. And that's the magic, is that it works. And when you plug those two, you'll find you'll solve, I think, figure out what a and b are, without any doubt. Then you'll still have c, d, and e, but you'll also have equations that are cubic equations. And by fiddling with it, you can go on and figure out what the values of c, d, and e. Easy to get rid of the plus 1 and the minus 1. You can do that. The others you're going to have to, will take a little more effort. Okay. Now, I sort of gave you an outline of it. Here is their decomposition. Okay? And here are the rules. And be sure you do the rules as they come. If you have some n of x divided by d of x, now where did they get those letters, do you think? Numerator, denominator, why not? Yeah. But both of those are polynomials. N of x is a polynomial, d of x is a polynomial. Now here's the deal. If you have that n of x and d of x, if n of x is a larger degree than d of x, or even the same degree of d of x, first divide. Do a long division of polynomials. If you can get away with synthetic division, fine, but most of the time d of x is going to be more complicated than that. So what you have to do is long division. Divide, if the degree of the numerator is greater than or equal to the degree of the denominator, do long division. That's what they mean by improper. N of x is an improper fraction, that is, the degree of the numerator is greater than or equal to the degree of the denominator, divide. Now, what you'll get is some polynomial, right? And then you'll get some new numerator, which is a degree less than b. Guaranteed, if you did your division right, the remainder is less than the degree of the divisor. Okay? And once you do that, you're okay. And here the n1 of x is less than the degree of d of x. Got it, if you did the division right. Then apply, then we go down and do these. Okay. So if that numerator is greater or equal degree to the denominator, first divide. When you divide, you'll get a polynomial, and then you'll get a remainder term which the numerator is lower degree than the denominator. Okay. Then you take that and come down. Then you factor the denominator. Okay? Now, as I said before, your factors, they can be messy, but hopefully they come into linear factors, maybe to powers, but still linear factors, and possibly an irreducible quadratic factor. Okay? So here's what they say the form will be. The most complicated form would be px plus q, and they would put in these coefficients, which really make it messy, but that they could be there, raised to some power, m. So that's your linear factors. Now, that m could be 1, okay, or could be other. You could have multiples of those, okay. And then you have some irreducible quadratic factor that you can't reduce any further, and that's to some n power, where this thing right here is irreducible. Okay. So for the linear factors here, okay, for every linear factor that you have with some power m, do an a1 over this to the first power, and a2 over that to the second power, a3 over this to the third power, all the way up to am times this to the nth power. Most of the time it's not going to be very many. Sometimes just 1, 2, 3. I can't ever remember doing a problem with 4 or more. So usually you're not going to have that problem. Just going to be a few. And then for the quadratic factors here, for every power that you have here, you have a bx plus c, b1x plus c1 over this to the first power, a b2x plus c2 over this to the second power, and keep going up till you have a b sub n x plus c sub n over this to the nth power. Now these subscripts here just mean these are the coefficients that go with these powers down here. Okay. So those will be your things. So you first got to factor, okay? And when you get your factors, most of them you hope will be linear factors. A few may be irreducible quadratics. Most of you hope not to have powers to them, but if they do, then you have a term for each of those powers. But with the coefficients, if it's linear, just being numbers. If they're quadratic factors, some linear combination of factors. Okay. That's the blah, blah, blah. Let's actually do one, thankfully, with just linear factors. They're pretty easy. How are we doing time? Huh? Yeah. Yeah, we leave it. 2:10. Yeah, 2:10, and it's almost there. So we'll start next time with linear factors. Okay. All right, let's see if we got some homework exercises out of that. I think we did. Or maybe not. No, I guess we didn't get far enough to do that, did we? Just based on what we did before, you could try number 3. Well, let's just wait. Do the ones from 8.4. That'll keep you busy, I think. And we'll do all these with 8.5. So like your question earlier, we're going to do 8.5, then numerical integration, and then using tables. Those are both fairly short. Well, numerical isn't that short, but using tables is. And then the improper fractions, integrals. I may just do a quick slideshow, but you won't be responsible for that on the test.
It's okay.
Okay, good deal. See you Wednesday.
And
now,
I was going to ask you, do you think we'll have school Wednesday?
Okay, we don't know for sure. That's exactly what I was going to say next. Especially pay attention tonight, because tonight I think is the worst night, because it's going to start raining. If it hasn't started raining yet, it doesn't look like it's anywhere close yet, but it is going to start raining sometime this afternoon or evening. And then as it rains, the temperatures are going to be dropping, and they're going to get below freezing, they say. I mean, down in the 20s below freezing. And so some of the rain will change to snow. Some of the water that's on the road is going to change to ice. And be careful tomorrow. Watch and see if Boston is going to be canceled. If we are, don't get on the roads. Okay? If we aren't, hopefully that means the roads are safe enough for you to get on. Okay? But It's not going to get very warm tomorrow at all. May get above freezing a little bit, but even more so, there's going to be a strong, cold, fairly dry wind. That may dry out the roads a little bit, and so it could be that Wednesday's going to be safe. But it could also be that it just melts some of the stuff from tonight, but not all of it, and then freezes again, and then it'll even be worse, because then it'll be sheet ice. So both days, pay close attention, see if the school's open or not.
Yes, sir.
We'll see you.
We'll see you.
Hopefully we'll see you Wednesday.
Luckily, this wasn't the summer.
What's that?
Luckily, we're not going to be out as much.
Yeah,
We're out this so many times.
I know.
The summer, this would have been.
Yeah. Oh, terrible. And it's bad enough fall and spring, but summer, yeah, that would have been awful. Okay, good deal.
We have a good one.
You too, thank you. Swap out books.